Hello, Mrs. Greathouse here. Welcome back from spring break. I hope you had a great time. We are going to jump into 11.3 net ionic equations and predicting precipitates. When we're looking at 11.3, you need to keep in mind that these compounds we are dissolving in water. And when they're dissolved in water, they're going to break up or dissociate into their ions, and all these ions are going to be floating around in the water. Sometimes a positive ion and a negative ion will come together with an ionic bond and make a solid precipitate, while the other ions that did not work in the reaction are going to stay floating around in the water. If you've ever been to any limestone caverns, you have been witness to this. These structures in the limestone caverns are formed from carbon dioxide converting calcium hydrogen carbonate into calcium carbonate. The calcium carbonate precipitates and forms the stalactites and the stalagmites that are so impressive. Okay, you know about word equations and skeleton equations and balanced equations. Today we're going to learn a couple new types of equations that you can write. A complete ionic equation is an equation that shows dissolved ionic compounds as their dissociated free ions. So in the reaction, silver nitrate plus sodium chloride yields silver chloride plus sodium ion plus nitrate, which is written as a skeleton equation here. That same equation can be written as a complete ionic reaction in the white box below. It shows all the parts of the compounds written as their ions, and then as a product we have a solid. The silver chloride precipitates out, where sodium and nitrate are listed as AQ and are still floating around in the water in their ionic form unchanged. Those ions that go unchanged are like the spectator ions. It's tennis season. Our ladies are playing tennis. If you go to watch the game, you're not involved in the game, but you're a spectator. Okay, spectator ions are ions that appear on both sides of an equation and are not directly involved in the reaction. Then we can talk about a net ionic equation, which shows only the particles involved in the reaction and is balanced with respect to both mass and charge. Our net ionic equation does not include our spectator ions. Here is our balanced chemical equation. Okay, our net ionic equation is on the bottom. It is balanced with respect to mass and charge. Okay, we have a positive and a negative on the left-hand side for that charge to be 0, and the charge on our compound on the product side is also a neutral compound, and that charge is 0 as well. So what happens is we are showing the silver plus the chloride to make the solid precipitate silver chloride. Okay, sodium ion and nitrate ion are not changed in the reaction, so we leave them out of the net ionic equation because they are spectator ions. Okay, so let's practice. We have reacting here in this photo aqueous solutions of iron 3 chloride and potassium hydroxide. Our problem tells us that we're going to get a precipitate of iron 3 hydroxide. we need to identify the spectator ions and write a balanced net ionic equation. So what you're going to start with is your balanced equation for the reaction. We have to remember to use crisscross to make our compounds like iron chloride. We have to know our nomenclature. We have to know the charge on our polyatomic ion. So you're putting a lot of information together. Okay, so our balanced equation is here. Okay, from there we can determine our spectator ions and write a balanced net ionic equation. Okay, so which are our spectator ions? They're the ones that are unchanged, that don't make the new precipitate, that stay floating around in the reaction. So that's going to be spectator ions are our potassium and our chloride. So now we need to write the balanced net ionic equation for the reaction. That only shows what's causing the chemical reaction, what's making the precipitate. So we're going to use our what we know about ions, and we know this iron is 3 plus from our stock ID system with the Roman numerals. Okay, and we know we're going to use our hydroxide, OH minus, to give us our precipitate, iron hydroxide. Okay, now we need to balance this for mass and charge. We have 3 hydroxides on each side. We have 1 iron on each side. Our charges are neutral on the left, +3 and a -3, and we have a neutral compound on the right. So there we are. You are probably wondering, how did you know that the iron hydroxide was going to form the precipitate and the potassium chloride was going to be the spectator ions? Okay, we learn all this from the solubility rules for ionic compounds. This is in a chart on page 344 for you. You do not have to memorize it. I will give it to you with any test. So key point, you can predict the formation of a precipitate by using the general rules for solubility of ionic compounds on page 344. Here's an example problem to predict the formation of a precipitate. Here's our question. Will a precipitate form when sodium carbonate solution is mixed with a barium nitrate solution? Okay, so written out here is the complete ionic equation. This is like a double replacement reaction. Our compounds are going to go into solution in the water, and they're going to dissociate, break up into their cation and anion. So we need to consider, what if an ionic bond were made between our outsides, sodium and nitrate? Okay, then we look in our chart, table 11.3 over here, and we see nitrate salts and chlorate salts. Any ionic bond that you make with a nitrate is going to be a nitrate salt. It tells us that this is soluble. Okay, soluble means that it's going to dissolve in the water, so that's not going to be our precipitate. But if we combine our insides, our barium and our carbonate, is that going to make a precipitate? So we look in our list, carbonates are at the very bottom. Okay, carbonates, phosphates, chromates, sulfides, and hydroxides. Most are insoluble. That means that they will not dissolve. So that is going to be our precipitate. To reiterate that, if your combination of anion, cation, say soluble in the chart, it will dissolve. If you look at the chart and that combination is insoluble, that means it's your precipitate. Thanks for listening. Bring me all your questions in class tomorrow.